In today's tutorial, we will develop a synthesis for this target molecule starting with this bromo-substituted olefin. So, thinking about starting from here and somehow getting to this target molecule, that usually doesn't work. This is clearly, it's too complicated. This is clearly a case where we start with a target molecule in the sense of a retrosynthetic analysis. And this will end up in a bidirectional analysis. So from here by retrosynthetic analysis to simpler structures and then approaching those simpler structures from that starting material. Oh, okay, you have a four-membered ring here, and how could we best achieve formation of four-membered rings? Photochemical 2+2 cycle addition reactions. Retrosynthetic analysis, then we clearly have two possibilities to form the four-membered ring. Either starting from this compound here a cyclopentene and here the olefinic chain at the ketone. So the six-membered ring has been disconnected. Or, on the other hand, disconnecting that five-membered ring. So that means this one and that one would be the strategic bond we have to break within the retrosynthetic analysis. Then the cyclohexanone remains intact, but the five-membered ring is disconnected together with the four-membered ring. So, and now we can compare those two structures with the starting material. We have a C5 chain, an olefinic C5 chain. Here we have that chain 1, 2, 3, 4, 5. Here also 1, 2, 3, 4, 5. Okay, fine. Well, attaching that chain to a carbonyl group, here is the strategic bond. This clearly brings us to a metal organic compound. The metal might be lithium or maybe a magnesium halide, magnesium bromide, grignard. No problem to get those organometallic compounds from, as you know, a halide like that. And this is then the nucleophilic center, delta minus. We need the electrophilic center. It's that one. And best in that case would be if we choose an carboxylic acid chloride. So, in this case, well, the reaction takes place not at a carbonyl group. The connection is alpha to a carbonyl group. So, that means alpha to carbonyl group, after deprotonation we have nucleophilic reactivity. This then, with the electrophilic reactivity, we can use that one. So, and just to show what would be the best way to synthesize that. Let's start with cyclohexane 1,3-dione having a base present, deprotonating and overall eliminating HBr. So deprotonating to the enolate, as a nucleophile it will react. And then we have already attached that chain to the right position. What has to happen here we have to perform a reduction process to the alcohol and then eliminating. However, having two carbonyl groups there, difficult to prevent that both are reduced. Well, we could introduce then a protecting group. What about an acetalization? And it turns out it's the right idea. Well, if we want to make an acetalization, a monoacetalization, well, we could, for instance, try a transacetalization with an orthoester. This is an orthoester of formic acid, and under these conditions we would observe that an acetal is formed, but under acidic conditions already an elimination reaction will take place, forming a donator-acceptor substituted olefin. And how do we get from here to there? As I said, we have to perform a reduction, for instance with sodium borohydride, reducing that carbonyl group here. Then we have an alcohol functionality here. There, that olefinic side chain. And now it's simply a hydrolysis under acidic conditions, which will hydrolyze this part to a ketone, and here then from the enol it will induce the elimination of that OH group, and therefore we have then the alpha beta unsaturated ketone. Thanks for listening.